raise your hand. There's a little function there to raise your hand or to send a question through the portal, the question and answer, and we can work on answering some of those questions. So if you have a question you want to answer, maybe at the end, you could put it into the question and answer with it, and there'll certainly be a session here that we're going to do that at the end. So let me see. Werner, hello from Germany. It's good, very good to have you, Werner. Thank you very much for joining us today. All right, and we'll open it up for questions both verbally and through messages at the end there. So, all right, so let's go ahead and get started. My name is Kevin Jameson. I am president at PureAir Filtration. Thank you very, very much for joining us this morning. We have people from all over the world joining us. Plenty of people from the US, Europe, Indonesia. So it's very, very nice to have everybody here. It looks like we have 34 attendees today. So it's very nice, and I appreciate everybody's everybody joining us and giving a little bit of time. Hopefully the information we give you can be of some benefit to you in the future. So today we're going to talk about selecting systems for wastewater odor control. And I do note in here that I am spelling odor two different ways, because we see that all around the world. Odor spelled one way. There's kind of more of a British way and maybe an American way as far as that goes. So let me adjust my screen here. I want to get a pointer so that I can point out a few things. There we go. Now my pointer's working, so I think we can move on from there. So again, I'm Kevin Jameson, president at PureAir Filtration. If you're just joining us, please feel free to put any kind of questions into the question and answer session. The section in the Zoom portal, and we're gonna you can also raise your hand if you have a verbal question that you want to ask as well. Looks like Wade just raised his hand a little bit here too. So Wade, let us know if you've got any questions. Sharon Patterson raised her hand too. So I can click on to allow you to talk if you need to with that, but at the moment we're just going to go ahead and get started. And if you have any questions, put them into the question and answer session, and we'll try to address most of those at the end. Okay. All right. Thank you very much, everyone. Let me work on getting my slides organized. So we will move to the next slide. So there are lots of things to consider when working with wastewater odor control, specifically any odor control, but especially wastewater odor control. What we have definitely found is that every odor control solution is very unique. All right. So if you think that you can order the same odor control system to handle every odor application you have, it's going to be very, very much wrong. There is a lot of customization that's required for these systems, and we're going to talk about that. At least there's a lot of customization that's required if you want them to work really well. And so, so we'll talk about that, about how these are all unique. One of the keys is that we're talking about total odor control, not just hydrogen sulfide control, all right? Because you'll find that there are lots of products that are on the market that are designed for odor control for municipal wastewater treatment, but they aren't comprehensive solutions, all right? They may take out hydrogen sulfide, and that's usually the predominant odor. That's the problem, but it's not the only odor. And so you can have a hydrogen sulfide removal system that might be 99.9% efficient in removing odors of a hydrogen sulfide, but it's not taking out all the odors. So just keep that in mind, and we're going to talk about how to make sure you're taking out all those odors. And then the key is to allow some flexibility, because this is a wastewater system, and the control of what coming into the wastewater system and how much is coming into the wastewater system and seasonality and all sorts of things you need to allow some flexibility in the design. So it's kind of impossible to know the conditions for a new construction. You can guess about what the odor is going to be like and such, but it's important to allow some flexibility in the design of the system for those unknown issues. And so it very well could be that you thought the odor was going to be a certain way, and it turned out it was going to be a lot different. And your system needs to be able to be adjustable to allow for that. And those changes in the collection system, even after installation, can be very important as well, too, because sometimes these odor control systems might be installed at the very early stages of a wastewater treatment line, at a sewage pumping station, and then that situation changes over the next decade or so with more construction and more people attaching to the wastewater system. And when we're looking at these systems, we need to allow for access and operation and maintenance. Of course, those are very important. An odor control system is only good as good as it is maintained. And while most of the systems that we promote don't require a great deal of maintenance, they do require a little maintenance periodically. And so we need to make sure we allow for that. And we need to understand the abilities to maintain once it's in operation as well. We'll talk about that too, that how do you know that the system's working well? How do you know those kinds of things? So these are some of the things that we're going to be talking about, but they're the things that you need to be thinking about when you're putting in an odor control system, when you're helping an engineer design it, if you are an engineer, you're designing it. If you've got a wastewater odor control problem, those are the things to think about to make sure that you get the proper solution. And of course, we're here to guide you. All right. Now, sorry, I've got to get my cursor moved. There we go. All right. So let's talk about types of odors. All right. So that's probably not a conversation you're used to having a whole lot. Let's talk about different wastewater odors, but it is important to talk about because, as I mentioned, not all odors are the same and they can be very different. So for instance, if you're dealing with a pump station, you may be dealing with a lot of fresh sewage odor. There may not be a lot of hydrogen sulfide because hydrogen sulfide is generated basically through the anaerobic process of sewage sitting around. Okay, so if you're dealing with a pump station that is dealing with sewage that just came out of homes within the past few hours, there's not going to be any hydrogen sulfide that's been created. There's going to be basically fresh fecal smell. Okay, and so we need to understand that because that's a different chemical. There's a different molecule which is causing that smell, and we need to understand what those smells are. All right, but in general, most of the odor issues we deal with, the primary odor by far is hydrogen sulfide, H2S. Without a doubt, it's smelled at very low levels. It's an offensive smell, and it's very, very, very commonly found throughout the wastewater wastewater process. So this is going to be a primary focus, but it's not going to be the only focus. There are other gases which are included in when you're dealing with hydrogen sulfide, and for instance, some of those are called mercaptans. Mercaptans are typically gases which have a basis in hydrogen sulfide, but they've been modified molecularly. Mercaptans, as an example, one of the mercaptans is intentionally added to natural gas. Natural gas doesn't have a natural odor. And so, but mercaptans is added at a very, very low level into natural gas so that you can smell a leak. Okay, so that's just a very interesting little trivia to let you know that smell of natural gas is actually an artificial smell that's been added so that you can smell any kinds of leak. Right, but these mercaptans do exist naturally in sewage wastewater odor control. So just keep that in mind when we're dealing with it. So if you've ever smelled a natural gas leak, then you've certainly smelled mercaptans before. All right, there's a whole family of other commonly found reduced sulfur compounds. So these have sulfurs in them and oxygen molecules and carbon molecules, just various compounds. And these are these have really typically very awful odors. This one is the dimethyl sulfide is an odor that is described as putrid garlic. Okay, so that's a horrible smell. But all of these have very, very bad smells at very, very low levels. Okay, and so and they're not easily removed. So I'll mention that to you. Another group of odors that you might come across are ammonia and amines. Ammonia specifically is typically related to certain processes in the wastewater odor control process, and it obviously is involved with tied into the nitrogen from urine within wastewater odor. But I want to mention to you, ammonia is a very, very special case because it is only smelled at high levels. Okay, so just the opposite of these gases, which are smelled at very, very low levels, ammonia is only smelled at very, very high levels, typically in the upper ppm levels. So maybe you could say 20 parts per million level ammonia is smelled at, whereas these are often detected in the parts per billion or even parts per trillion level here. So I want to mention to you, we get lots of inquiries where people want to control ammonia, but very often ammonia can be controlled by just diluting it with more fresh air, because it can, once it gets below about 20 parts per million, you're not going to smell it, even though it's there. And then some other odors that could be there are volatile organic compounds. So these would be like solvent type products, typically byproducts of maybe an industrial process that's upstream, typically not a big concern in wastewater odor control. So let's move to our next slide. So these are some of those same odors that we were talking about, and their formal name, the description of their odor, and their odor threshold. So if you're not used to odor threshold, the term odor threshold, that means what is the typical level that the typical human nose can begin to smell these odors, okay? And keep in mind that human noses are very, very different all over the place. My wife has a much, much better nose than I do. So some people can smell these at lower levels and some people can smell these at higher levels. Some people are extra sensitive to them, but generally these are considered the norms for the typical odor control. So hydrogen sulfide, the odor that we're typically used to seeing, can be smelled at 3 parts per billion, very, very, very low levels. But here ammonia, here 17 to 50 parts per million is that range. Very, very interesting. And here mercaptans are in the parts per trillion level here. So you can see that's why that mercaptan is used in natural gas, is because it does have this skunky smell to it, and it's smelled at very, very low levels. So you can detect it in a natural gas leak very easily here. So again, these are all offensive odors. Sometimes they're called malodors here, as we described, and generally they're all smelled at pretty low levels except for ammonia. All right, so how do we know what odor levels we have, right? So, you know, here Kevin's telling us that it's important that we know what the odor levels are. So how do we measure that? Well, there are some tools to do that, and I'm going to introduce some of these to you briefly, and we can work with you in further detail about this. One of the most useful tools, for this, is what's referred to as an Otolog or an Acrolog. Now, these are two different brands of instruments. Otolog is the original industry product, which was adopted by many people. I hate to say it, that they've gotten a little behind in the times as far as their electronics. And another company has come around by the name of Acrolog. Acrolog has a fantastic product, similar to the Otolog. And this is a device which has, you can even have cellular connection to it and such, but it's basically about the size of a soda can. And you can tie a rope to it and lower it down into a wet well to it, and it will collect data in regard to odors. Now, there's a hydrogen sulfide one that's available. I believe there's an ammonia version that's available, but it collects lots of data. Hydrogen sulfide, however often you want it to, but typically every 5 to 10 minutes, it might take a reading, and it will collect that data. And once you have collected all the data you want, which typically we'd like to see about a week's worth of data so that we can see what the odor looks like day and during weekdays and weekends and at nights and such, then you can download this data through a Bluetooth connection to the software they provide and really provide some great information. But it also collects information about humidity and temperature, some other good information just to have while it's in there. So I can't tell you enough about how great this device is. And there's different versions that measure at different ranges of odors, part per billion level units, as well as part per million level. And so this is a really, really useful device for measuring hydrogen sulfide or ammonia. Now, it's not going to do anything for the reduced sulfur compounds, but it at least gets you some good information about the majority of the odor, the most likely majority of the odor. There is another device called the Jerome Gold Film Analyzer that is really the gold standard in the industry for measuring part per billion level H2S. But this is a device where it's it's far more expensive. It's considered very, very accurate. But in general, you would carry this device around and take samples in different areas. And so PureAir has a couple of these devices as well. I want to mention to you that PureAir also makes these devices available on a loaner basis to our independent sales representatives. And so at times, if you are a registered PureAir sales representative, we can make these devices available to you at no cost, so that you can do some work in trying to find out what your odor levels are. We have these available in our Amsterdam office, and we have them available also here in the US. Unfortunately, it is more difficult outside of the US, Canada, and Europe to get these moved around because of customs and such, but we can work with you on trying to figure that out. Also, another very often used tool to determine exact amounts of odors and exact types of odors is to use Tedlar bags. And so what is actually happening here is that you'll use a special bag with a valve on it, and you're actually going to fill the bag up with some of the odorous air from the system. All right, so you can use a pump, and you can put a tube down into a space, and you can pump air from that space into the bag, and then you send the bag to a laboratory which does analysis on that air. So it's very unusual, and you should see the faces at the FedEx store when you walk in with a box, and they go to pick it up, and it barely weighs anything, and they say, "What's in here?" And you say, "Air." Well, that's exactly what's happening. We send these bags of air to the laboratory, and there's generally two types of tests that can be done, and it's two different types of laboratories. So the first type of test is actually a spectral analysis of the gas. So they're going to actually sample it and run it through a spectral analyzer, which is going to tell you the exact gas and the exact amount of gas. All right, so that's very, very valuable. You get a long list of the gases that are in there and at what concentration. So that's a really nice analysis to have. It tells you exactly what was in the bag. The other is an odor panel test, and typically this is a larger bag. It's usually a 10-liter bag, where you only need, I think, a 1 or 2 liter bag for the spectral analysis. The odor panel is actually a panel of people with trained noses and certified good noses who will actually take the air that's in that bag and they will smell it and they will adjust a dilution to that smell until they can no longer smell the air that's coming out of that bag. So they'll dilute it, 1,000 times dilution, 500 times dilution, 100 times dilution until they begin to smell it. And when they begin to smell it, they'll characterize it and tell you what kind of odor it is and what category it is. But that they'll actually give it a measurement of odor units. An odor unit is how many dilutions is required with fresh air in order to not smell it any longer. Okay, so one odor unit would mean that you were able to you were able to dilute it with 1 unit of fresh purified air and could not smell it. Okay, 1,000 odor units meant you had to dilute it 1,000 times before you couldn't smell it any longer. All right, so it's a good, though it's a subjective measurement. There are people who are trying to smell that. These are expert people, and it's a multiple people that do this test so that you get a combined score. And basically from there, if you gave them an inlet and outlet reading of it, you would be able to tell how much the overall odor improved. So it's a nice test, and it's a formalized ISO test with it. So we can give you further details about that if you'd like. Now, the one disadvantage of this feature is the bag of air that's there is only giving you a sample in time, right? So you took the sample of air at noon. Well, it tells you what the odor was like at that period of time. It doesn't tell you what the odor was like later on, okay? So you have to be a little bit careful when you're looking at the data. The Otologs or the AccuLogs give you really good measurement of hydrogen sulfide over time, and the Tedlar bag testing gives you spot samples of this. So, but with the two, usually you can get some really great information and put together a good solution. Now, let's not forget about the good old nose when doing this as well too, because that's what's being used to measure these odor units. And just keep in mind that your nose knows well whether the odor is offensive and whether it's improved and such. And so it's important to know that. But I will say that generally hydrogen sulfide has a characteristic that it's not detected over 30 parts per million. So if you actually had hydrogen sulfide at high levels, the human nose can't smell it over 30 parts per million. So just be aware of that. But of course, you can always tell whether the odor is improved or not by just using your nose. All right, so the key is that when we're taking a look at all these odors that we're dealing with, there are many types of odors, and the level of the mix can be constantly changing. So we need to keep that in mind. Offensive odors detections can be extremely low in the parts per billion or parts per trillion level. Different odors need different treatment. So we're going to talk about that a little bit more here, but no odor can be the same. If you have an odor control manufacturer that tells you that that any odor is basically can be treated the same, that their system, no matter how it's configured, handles all odors, I wouldn't believe that. All right, these are all different molecules and they all have to be handled in different ways. System designs really need to be effective to remove all odors. If you have people in a neighborhood who are complaining about a smell, and you put in an odor control system that just removed the hydrogen sulfide, but it still has a smell, they don't care whether you reduce the hydrogen sulfide. All they care about is, was there an odor before and is there an odor later? So that's one thing that's very important to understand, is that you need to understand there's lots of odors and we need to try to work on getting all of them out. All right, so taking a look at odor control technologies, what do we have available for odor control technologies? Well, we're going to briefly look at 3 odor control technologies today. Adsorbent systems, and that is a primary product for our company, PureAir Filtration. We're going to take a look at biological systems because biological systems have a lot of great fit in the industry. And we're also going to briefly talk about chemical scrubbers. Now, I'm no expert on chemical scrubbers, but we're going to talk about it because they're available and they do work. There's a lot of maintenance to them and such, but in certain instances, chemical scrubbers can be the right fit. But all of those systems have one thing in common. They all need actual physical chemical contact in order to remove the odors. And that's the mechanism it's the mechanism that we use that separates those technologies. So the key with all of these technologies is you have to be able to capture the odorous air, run it through a system, have some type of contact in the system. Some systems need more contact, some systems need less contact, depending on the technology. And it's that mechanism which separates those technologies. So just very briefly, when we're taking a look at selection criteria, these are some of the things that you should look at. We're just going to run through very briefly. The efficiency of the system, that's very important. There's going to be no system that's 100% efficient. Now, there's plenty of systems that are 99.9% efficient, but typically you're not going to find anything that's 100% efficient. Reliability is very important. Initial cost, of course, is very important. Operating costs, of course, very important. Footprint, space, height as well. Sometimes customers don't want a very tall system because it stands out and doesn't look very good. Ancillary buildings, systems, and controls. What else is needed to support the system? We have some customers who are in very, very cold environments, and they end up needing to put some of these systems into buildings to prevent them from being, just depending on the technology, to keep them from being in the kind of Arctic conditions. And so, that obviously drives the cost of the system way up when you're building a building for the system to be put in. Of course, my favorite is maintenance and operation concerns. Sometimes those aren't considered very well, and there are some systems which require a significant amount of maintenance, and that should be known up front, okay, when you're looking at that. There are some maintenance operations which are better than others, and you should really understand the maintenance capabilities when you're looking at technologies, because to introduce a complicated technology to a maintenance operation which isn't very sophisticated can be very problematic. Also, what about hazardous chemical handling? All right, so if there's a type of a system that uses hazardous chemicals, what's involved there? Of course, aesthetics are important, and of course, noise is very important as well too. If you're installing at a pump station that's right next to a home, you may fix a odor problem but create a noise problem, and that's not going to go over very well for the neighbors. So what type of technology do you use? And we'll come back to this chart in a little bit here, but what kind of technology do you use for various levels of odor and such? This is a chart that was put together. It's very general. I don't want anybody to think that there's exact numbers to any of this. This depends on a lot of different factors. And I have not included the chemical scrubbers in here with it. But so we have various zones where you could kind of take a look at what depending on your airflow, and depending on your odor level, and this is basically H2S levels in parts per million, because that's generally what drives the main design of the system. What technology would you look to use? So if you've got fairly low levels of odors, engineered adsorbents or activated carbons would be, for low flows and low odor levels. Just plain activated carbon would be fine, and of course, engineered adsorbents would work very well. If you've got higher levels of H2S, typically activated carbon is not going to be very good because it doesn't have a high capacity for hydrogen sulfide. but some of the engineered adsorbents have very high capacity. We're going to talk about that in a little bit. So if you get into kind of that 20 up to about, say, 20 parts per million coming into the system, engineered adsorbents work well. In that range of kind of 20 to 100, now you're talking about using some other technologies, because it would be very expensive to use engineered adsorbents for a high level of odor. So maybe you're going to use a combined technology of a low-cost scavenger plus engineered adsorbents, or maybe a biofilter or bioscrubber. Or you might be taking a look at scavengers followed by engineered adsorbents there. So, and then when you're getting into much higher levels of odor, let's call it 100 parts per million or above, then you're generally talking about needing to use a bioscrubber. And we're going to talk about the difference between a bioscrubber and a biofilter very shortly. That's kind of the terminology we use between two different similar technologies. But generally, a bioscrubber is not going to take out all the odors. And so it's very important to tie it in with an engineered adsorbent system to catch the remaining odors that come through. So these are just some suggestions, some general rules of thumb. There's lots of things that drive it, but this is kind of where we start from when we're taking a look at technologies. So let's take a look at adsorbent systems. So adsorbent systems, in general, there are three types of adsorbent systems. Adsorbent systems can be activated carbon. Now, activated carbon is basically charcoal, which has gone through an additional processing step, and it serves to capture these odors and capture a lot of different odors. So it's good for general odor capture. It's really, really good for volatile organic capture. But in general, it has a low capacity for inorganic odors. So activated carbon, because of carbon molecules, has a really strong affinity for other gases with carbon molecules, but has a low affinity for typically non-carbon molecules. And so there's various calculations you can make for different types of odors and how well they're going to work. But in general, activated carbon also allows for some of these odors to escape by desorption. And there's no way to measure the remaining life of activated carbon. So activated carbon is a good product, especially for removal odors of commercial applications or for volatile organics, but generally it's not a great product for municipal odor control. So what about the category of adsorbents called engineered adsorbents? Right. Well, engineered adsorbents are similar to activated carbon. Some of them actually use activated carbon in the formulation, and they use a chemisorption principle. This chemisorption principle targets particular gases. We're going to take a look at some of these in a little bit, but basically it's modified to target particular gases and have a very high capacity for those gases as well too. It's also a permanent reaction, so you don't have to deal with any of the desorption what might occur with activated carbon. And then the last area of adsorbents is a field called scavengers. All right, and these scavengers are basically low-cost roughing adsorbents for reducing H2S levels. All right, they're not going to be as efficient as engineered adsorbents, but they're going to be lower in cost. And if you've got a higher H2S level, then it's going to help trim that level down, and then you can use engineered adsorbents to remove the rest of it. So let's talk about those a little bit further. So how does gas phase filtration adsorption work? So various adsorbents are used which are porous. These pores are very small, typically just larger than the molecules that are being adsorbed. And then molecules find their way into the pores and they're trapped inside. Weak molecular attraction holds the molecule into the adsorbent. Okay, so it's kind of like cubby holes for molecules with it. So the principles used here is a process called adsorption. Okay, adsorption with a D means that gases go into, and let's just call it activated carbon, because activated carbon uses the principle of adsorption. These gases go into the activated carbon and they're held in like a sponge, okay? So just think of it, activated carbon as being a gas sponge. These gases go inside and they go into the activated carbon. In the right conditions, though, just like a sponge, you can take a sponge and a dry sponge and you can put it in a little puddle of water on a table, and that water is going to go into the sponge. Activated carbon, that works the exact same way. Those gases go into the pores of the activated carbon. They travel into the activated carbon. They find a little home in one of those pores there, just like water travels up into a sponge and is captured in the pores of the sponge. But just like a sponge, if you wring that sponge, the water comes out. Same thing with activated carbon. Now, that wringing of the sponge would be like activated carbon being heated or being hit with a high humidity, or a larger gas coming in and bumping out a smaller gas with it. All right, so it's not quite as rapid as wringing a sponge, but adsorption is definitely can be reversed, and those gases can be desorbed from activated carbon. In fact, there's very specific types of system that are called pressure swing desorption vessels with activated carbon, where they allow the carbon to get filled with the gas, and then they put that under a vacuum and they suck all those gases out of those pores, right? And then that carbon is actually regenerated to some extent where it can be used again. So just keep that principle in mind when it comes to activated carbon. It's like a sponge. It holds those gases and then it can release them later on. Chemisorption is kind of a subset of adsorption. Chemisorption, those gases go into the pores, but then they go through a chemical reaction, and that chemical reaction binds those gases into the adsorbent permanently, and they are in there as a solid, no longer a gas any longer, and they do not come out. And so the nice advantage of chemisorbents is that it's a very, very permanent reaction, and you don't have any gases that are coming out the backside of the system on a periodic basis. So that's one of the keys with chemisorption. The difference between activated carbon and engineered adsorbents is the difference between adsorption and chemisorption. All right. Here is a microscopic view of those pores of activated carbon. Okay, so if you look at it, you know, this is of course a atomic microscope showing you these pores, and so molecules are going into these pores. They're traveling down further into the activated carbon, and they're actually sticking to the side of these carbon. This is all carbon molecules, and those molecules are sticking there. So it's using the chemical principle of the van der Waals effect, all right, where molecules stick to each other, and that's what's actually happening. There's no let's call it chemical reaction that occurs. They're just stuck to each other inside the activated carbon. The thing that's so amazing about activated carbon is that 1 gram of activated carbon, let's just say the amount that you can hold in the palm of your hand, just a small amount, has the surface area of a soccer, sorry about the typo there, a football or a soccer field with that. So if you measured the surface area of every one of these pores and counted up every one of these pores, and you could lay that flat out on a soccer pitch, a football field, it would cover the entire field. That is how much surface area is inside of activated carbon. It's absolutely unbelievable, and that's why it's able to capture so much in regard to gases. So let's talk about, well, we already kind of talked about this. So for adsorption, it's a physical process. We're holding those molecules in there and they can be released. Examples, activated carbon, it's reversible. The chemisorption process, some examples are permanganate impregnated aluminas, impregnated carbons, catalytic products. All of these are irreversible. So just a little better view of activated carbon. One of the things I'll mention to you about activated carbon is there are lots of different types of activated carbon because there's lots of sources for the charcoal, which makes activated carbon. So if you're familiar with charcoal from barbecuing, it's basically the same thing. You could make the charcoal from wood, you could make it from coal, and a very interesting one is there's a very large market for coconut shell activated carbon. Okay, coconut shell activated carbon happens to be one of the best activated carbons for the capture of volatile organic compounds. It's very poor for typically hydrogen sulfide, but it's very good for volatile organic compounds because of its pore sizes. And that's the difference with all of these charcoal, with all of these various base carbon charcoals, coal versus wood versus coconut shell or nuts or other sources of carbon. The size of those pores vary depending on your source with that, okay? And so the various sizes of those pores are better or worse for capturing various sizes of molecules, right? So small pores are typically good for small molecules. Large pores are typically good for large molecules. Also, large pores are very good for using impregnates on the activated carbon for capturing other gases as chemisorbents too. So generally, coconut shell carbon, which has very small pores, is not a good carbon for impregnating and turning into a chemisorbent, while coal-based products are much better for impregnation turning into chemisorbents. So activated carbon is charcoal that's been activated with some steam, typically used, it's typically steam, which opens up all those pores. Typically the carbon, it's 95% or more pure carbon. All right, so it's all carbon molecules that are just combined. There's about 5% impurity in it, which is basically just minerals and such that the original organic product was needing to use. Carbon has this high molecular attraction for other molecules, especially other carbons. It's great at VOC removals, poor H2S capacity, can release off-gassing. We brought that up already. There's no reliable way of measuring how much the activated carbon has been used up, how much has been captured inside of the activated carbon. So that's kind of a little difficulty with using activated carbon. And it comes from many different sources, as I mentioned to you. All the time we're hearing about other new sources of activated carbon, but the primary ones are various coal sources, coconut shell, and wood. Here is kind of a micrograph that's used in a lot of presentations. I'm not sure who the original source is, but I've stolen it from others who have stolen it, I think. But generally, this graph shows you these pores, and the pores could start off larger and they head down and get smaller and smaller. These in these areas we would be considering micropores, and so these small molecules go down and get caught in the micropores. The larger molecules would get caught in the larger pores, which are typically called macropores. So there's macro, meso, and micropores, and various carbons can be graded based on their percentage of micro, macro, and mesopores with that. So just depending on what you're trying to use the carbon for, you would select the various carbons for that. So we'll briefly discuss regeneration of carbon. I kind of mentioned this to you before. It is something that can be done. It is far less common to see regeneration any longer, but it is something that can be done. I just want to bring it up. PureAir typically isn't involved with it, but it's good that you know about it. So there's two types of carbon regeneration. The most common is kiln desorption regeneration, all right? And that means that you take activated carbon, and this can only be plain activated carbon, which doesn't have any impregnation on it. So none of the engineered adsorbents. You can take the plain activated carbon and you send it to a site which has a furnace, and they run this activated carbon through the furnace at a temperature which doesn't consume the activated carbon, but heats it up enough to drive off the adsorbed gases. And then they typically burn off those adsorbed gases, and then they can return it to use. Typically, this is the product that comes out of a kiln is typically a less preferred product because it's been used already. It typically doesn't have the capacity of the original product because you typically can't get out everything that you put into it. But it is a way to recycle the product. So that is, if you have an application, especially if you're capturing a lot of hydrogen, a lot of volatile organic compounds, that is an option for you to send your activated carbon off for regeneration and then bring it back and keep reusing it that way. And you can get a number of regenerations out of it before it can't be regenerated well again. Generally, you're going to lose some capacity each time you regenerate it. And so, you probably add some new carbon to it each time you do it, and you kind of keep it going from there. But yeah, you might say, it's hard for me to say, but you might lose 5 to 10% capacity in each regeneration. Now, there is also the possibility of what's referred to as in situ water regeneration for activated carbon. This is a very special product. Generally, it's for air purification, specifically of hydrogen sulfide, and really only hydrogen sulfide. What happens in these activated carbon systems is this special carbon absorbs hydrogen sulfide, and then periodically the system is shut down and closed off and filled with water and repeatedly rinsed. And the hydrogen sulfide will actually react with the water and convert itself to sulfuric acid. And you can actually measure the pH of the water as it's drained, and you can regenerate that. So the first washing will have a higher acidity, a low pH, and then you'll just repeatedly keep rinsing it until you get your pH doesn't change any longer. You hopefully get the same pH going in that comes out, and then you can allow the carbon to dry out and then start the system back up, and it works. So that works really, really well in a laboratory. But unfortunately, from the standpoint of real life, what ends up happening is all those other gases which are captured in the from a wastewater odor control application, all of those other gases do not get washed out. So in a laboratory, this works really great, where you're injecting only hydrogen sulfide in and you're washing out only sulfuric acid. In the real world, other gases get captured in this activated carbon. They don't get washed out, and it reduces your ability to reuse the carbon after it gets washed. And so typically you're losing very high percentages after each washing. We've generally seen 20% or more capacity that's lost. And so if you start off with 100% capacity in the beginning, and by the way, this doesn't really have very good capacity in the beginning anyway, you start off and then you lose 20%, so you're at 80%, and then the next time you regenerate it, you're at 60%, and then you're at 40%. Well, after a while, you're washing it really often, and it just isn't beneficial to it. So we don't see this product very much in the market any longer, certainly not in the North American market. We don't. There are a couple pockets of the world where it still exists. It was an interesting product, but unfortunately, unless you have an H2S only application, it's not really very good. All right, so let's talk about chemisorption. We've moved on from activated carbon. Chemisorption is, again, where we have taken an adsorbent and we have put a chemical on there, and it's going through a chemical reaction to focus on particular gases, or could be broad range gases. So there are two parts of an engineered adsorbent. There is the substrate, right? And that's what creates the pores. And then there are the impregnates. That's the chemical that we put on there in order to go through the reaction. All right. So the various substrates we have to work with are activated carbon. As I mentioned to you, activated carbon is the king of porosity. Generally, the kinds of numbers we talk about are about 1,100 square meters per gram. That's a fantastic number. Really, really, really high number. All right. Another is alumina. which is activated, or it's activated alumina, which is aluminum oxide. Still a great product. It's generally inert. So we can put lots of different chemicals onto this alumina for reaction. And it still has really good capacity as far as surface area and porosity, but it's only about a third of that of activated carbon. So that just tells you how great activated carbon is for porosity. Alumina, which is still a great product, has about a third the capacity. Zeolites, there are a broad range of zeolites, but the primary zeolite that's looked at here is a naturally occurring zeolite. It has some porosity. It has generally about a third the porosity of alumina, so about a tenth or 1/9 that of activated carbon. The advantage is it's really, really cheap, and so for some non-critical applications, it can be used, especially for very cost-sensitive applications as well. And there are some other products, some other clays that are similar to zeolites, which can be used for some products as well that provide some porosity. Generally, the clays are not going to be very porous. They'll have some porosity, but they won't be very porous. And so these are the substrates. That's what's going to hold the chemical, which is going to go through the chemical reaction. And then what are the chemicals we're using? Well, if you're taking out acid gases, then you can use a caustic product, which will react with the acid gases. If you're trying to take out ammonia, then you could impregnate it with acid, and that acid will react with the ammonia and take the ammonia out. If one of the broadest range ones is this purple product, if you go back to your high school or college chemistry days, there was a product which everyone always had a difficult time pronouncing called potassium permanganate, and that's a product which, of course, PureAir is very famous for. And it's this purple color product. The potassium permanganate is typically put on alumina. Sometimes we'll put it on zeolite as well if we have a customer that has a non-critical application. And that is a broad acting oxidizer. So anything that can be oxidized will be oxidized by the permanganate. So this is a really nice broad range product. It also has the nice advantage that it changes from purple to other colors, typically brownish or brownish white when it's used. So it's a nice indicator of consumption. And then the other one, which is very, very nice, is if we add some catalysts to some of these substrates, especially activated carbon, we can produce some products with extremely high capacity for particular gases, and really hydrogen sulfide is the big one there. So we've got some products that have capacity of about 66% by weight. So that really is like a sponge where it's capturing a tremendous amount of hydrogen sulfide compared to the actual weight of the activated carbon that it's on. So those are engineered adsorbents. And these are just some more specifics about it. This is the Sulfazorb XL catalytic type product, 66% by weight, really phenomenal for H2X applications. I'll mention that the capacity is actually more than 66% by weight, but the product removal performance degrades significantly beyond that. But we've seen this product have some just, even though it might not be as efficient after 66% weight, it still captures some H2S, and it's really, really fantastic product. Especially wastewater industry, it really has its use for taking hydrogen sulfide out. The permanganate impregnated aluminas, sometimes it's referred to PIA, but we have both 8 and 12% concentrations of permanganate onto the alumina. So it's activated alumina impregnated with permanganate, typically potassium permanganate. There's also one called sodium permanganate, which we can use just depending on the application. Again, it works on oxidation. The really nice product is it's completely non-combustible, all right? So there have been some concerns in the past about the use of activated carbon and carbon bed fires. We won't go into that too much here because it's kind of an old problem. But if you use an impregnated carbon, especially if it's caustic impregnated carbon, which was more common to be used in, let's say, the prior century, there is a substantial chance of a fire. I'm not going to say a major chance, but there are very documented cases where caustic impregnated carbon has caused a carbon bed fire and a couple really big disasters. And so customers are very, very focused about not allowing that to happen again in the future, and using products that are completely non-combustible is very, very favorable with those customers. So we should definitely, well, one thing I'll mention, you definitely want to avoid caustic impregnated carbon. It works well for odor control, but the potential for carbon bed fire is very dramatic, of course. And then I mentioned that color change for this product. Now, here's an interesting one that we can do. A blend of carbon and permanganate impregnated alumina. We use this as a polishing media to capture all of those other odors after our catalytic sulfur-adsorb XL takes out the hydrogen sulfide. So if you blend activated carbon, again, which is charcoal, so keep that in mind, it's charcoal, it's just gone through an additional step. But if you blend it with our permanganate impregnated alumina, that end product blended still meets Underwriters Laboratory fire rating. It's called UL 900. And so even though you are using activated carbon, you still get a fire rating for that product. So that's a very nice product. A low chance of off-gassing, because if you do get any off-gassing from the carbon, typically the permanganate alumina, impregnated alumina is capturing it, and you still get that color change. So these purple balls will turn to a brownish white. So you could take a little sample of it, know whether it's being consumed. So I'll mention that this blended product is very, very powerful for capturing those other odors inside an adsorbent system. So the last area of adsorbents that I want to talk about is scavengers. So scavengers are products which are kind of a low engineering product and have a low cost. So this scavenger, this is actually our product, Sulfadsorb Fe for iron. Sulfadsorb Fe uses iron oxide to react with hydrogen sulfide. And this has generally a pretty high capacity, but it's not as reactive to hydrogen sulfide, as quickly reactive as some of our other products. And so generally it requires more contact time or a lower stated efficiency. But what's really great about this product is that you can use the product to, if a customer had an application where he had elevated levels of hydrogen sulfide and he didn't want to put in other technologies, this will trim down that level of hydrogen sulfide to a more manageable level. And then that more manageable level is where you could use some engineered adsorbents to take out the remaining amount of hydrogen sulfide. So scavengers would very often be used in a two-stage system where the scavenger takes out, let's call it 90% of the hydrogen sulfide at a lower cost. And then engineered adsorbents would take out the remainder, as well as any other odors. This is also used for our biogas product line. All right, so biogas is where you're basically taking methane or natural gas from various sources, landfills, farms, digesters, etc. And you're needing to purify that biogas. We use this product typically to take out thousands of parts per million of hydrogen sulfide down to very, very low levels, so that you can turn that gas in a biogas environment into natural gas, and then you can either use it for fueling natural gas vehicles or for generating electricity, etc. So these scavengers are also very, very heavily used in the biogas industry, and they're newer to the wastewater industry as far as using them, but they have a really nice place. So let's take a look at systems now. So here's a typical system, and I chose this one because this one happened to have 3 different colors of 3 systems, so it allows you to understand what the different pieces are. So a typical adsorption system that has adsorbent media in there has basically, let's call it 4 components. There's an inlet mist and grease filter. All right, now, does that have to be there? No, it doesn't have to be there, but we strongly, strongly recommend it, especially for wastewater applications, because these systems operate typically 24 hours, 7 days a week, 365 days a year. And a wastewater environment typically has very wet air coming into it. Now, wet, I'm not referring to humidity, but I'm talking about droplets of water. And if you're running these systems 24/7, eventually you're going to be pulling in a lot of water droplets into the system. So it's very, very important to have a high efficiency mist and grease filter here to capture those contaminants and then drain them out or capture them inside of the filter pad that's inside of here, so they don't collect inside the fan, so they don't collect inside the adsorbent system. This adsorbent system is filled with adsorbent. That adsorbent does not like to get wet. And so we want to try to keep those water droplets. So the water droplets we're talking about are fog-sized water droplets that eventually, when you operate 24/7, accumulate to a great deal of water. So having a highly efficient mist and grease filter at the entrance of the system is very important. Of course, there's a blower. The blower can either be before the system, or we do sell some models that have the blower that's on maybe on top of the system or on the outlet side of the system. The advantage of having the blower on the outlet side of the system is it's seeing the purified air, so you don't have to have as robust a blower. The blower if it's on the inlet side of the air between the mist and grease filter and the adsorber, this needs to be very robust. It needs to be, this is a highly corrosive environment between the water and the hydrogen sulfide that will be combined to make sulfuric acid. So typically these blowers need to either be polyethylene or fiberglass. Typically fiberglass is a standard for it. And so these blowers can be very pricey because a fiberglass blower is very expensive. But to use a steel blower here, I've seen that happen, and the blower lasted for about 2 months before it just completely degraded there. Even 304 stainless doesn't hold up very well. 316 stainless can. And so the selection of the blower here is very important. The vessel. So the vessel is a tank, and it's filled with adsorbent media. We see a lot of engineers really, really focus when they write a specification. They'll write a 20-page specification for an odor control system. 19 pages will be about the vessel and the fiberglass and exactly how to build it. We don't understand why, because it's really not a critical application. This is really just a simple vessel that's holding the adsorbent media. Of course, it needs to be strong enough to support all that adsorbent media. There are great systems. This system happens to be made out of high density polyethylene. It holds up fantastically in the weather. It's very low cost, but we also sell systems that are made out of fiberglass, much more expensive, but do certainly hold up very well over time and are very strong. We even have customers that order systems out of stainless steel, typically 316 stainless steel, which are of course very expensive, but they have their reasons for ordering those with it. So the key is there's lots of different materials, and all those materials have different price points and lead times and such. And PureAir offers those various options for materials of construction and such with it. So just to get everybody an idea on timing, we're in slide 25 of 40. So we're a little bit more than halfway through, and probably 2/3 the way through, I think. So there are small systems. I mentioned these systems that have the fans on the outlet. So these systems have a mist and grease box, the vessel, all of this is made out of HDPE, and then it has a cast aluminum fan, which is corrosion resistant, but I wouldn't want to put that in the inlet side of the system. It's cast aluminum is corrosion resistant, but it's not corrosion proof. And so these are very, very nice, what we call economy systems, not highly customizable, but very, very effective. Your performance kind of on a ratio of amount of adsorbent media for overall price of the system, this is your most economical system. We have horizontal flow systems. This is referred to as a packed bed system, a PBS system. This is all integrated together in one fiberglass housing. So this is your mist and grease filter. You've got adsorbent media beds here. This is a 2-foot bed. This is a 1-foot bed. So you've got 2 separate beds that are held in between screens here. This is a very nice system where you could have 2 separate adsorbent medias that are independent beds. So you could change out this bed without changing this one. This is the blower section here. It's an internally housed, very, very quiet blower, and then an exhaust stack on top. So this is a custom fiberglass PBS system, packed bed system we have. Let's take a look at that mist and grease filter. So here's an example of us testing a mist and grease filter going into a stainless steel system. So you can see the fog that's going into the system. That's the kind of water that this type of filter removes very, very efficiently, typically 99.9% efficient at water droplets even down to 2 microns. So this is what this mist and grease filter pad looks like. You've got a stainless steel mesh along with some glass fiber mesh, and then some further stainless steel mesh, basically just to make sure the filter is reversible. And the mists, the water vapor is going to be captured in here, and it will eventually drain down to the bottom. There's a drain at the system, and that water will be captured in there and drain out of the system. The grease will be captured in here, and these filter pads, which are permanent filters, but do periodically have to be pulled out and maintained, can just be washed in a hot detergent bath and a pressure washer, and then they're able to be reused. So it's very, very, very common for customers to order a spare set of these filters. So they always have one set that can be put into the system clean while they're taking the other set off to be cleaned. Customers always want to know, how often do these have to be cleaned? Typically every couple months, maybe. It depends on how much. It's really the grease that has to be, and dirt that has to be washed out. So it depends on how much grease and dirt that you have coming into the air of the system. That'll tell you how often you have to clean it. This, if we go back to here, you can see a nice Dwyer magnehelic gauge here, which is measuring the pressure across the mist and grease filter. Our local Dwyer representative is joining us on the call today. And this will measure the mist and grease filter pressure drop. And so when that pressure drop, when the filter gets dirty, the pressure drop will go up. And when it reaches about 2 inches of water column, we typically recommend that it gets cleaned before it reaches 2 inches of water column. So that's there to tell you when to clean this filter out. Very, very important. This filter really protects the adsorbent media. I can't stress to you how many times that we have retrofitted a competitor's system who did not put a mist and grease filter on their adsorbent system. And we have customers whose adsorbent media life is 5 times longer than it was with the competitor when they changed to our adsorbent and they added our mist and grease filter, and they got 5 times longer life out of it. That's how important this mist and grease filter is to these applications. So I can't stress it enough. And the cost isn't really that much for it. It's just much better just to put it in, even if you're not sure if you need it. So one of the other parts that we promote very heavily in regard to wastewater odor control is using multiple adsorbents to capture all of the odor going through the system. So in these cases, you're seeing 2 different media compartments in these, where one compartment is typically going to be our H2S catalyst engineered adsorbent that's going to capture the hydrogen sulfide, especially if the majority odor in the application is hydrogen sulfide. And then we'd have another compartment which would hold another adsorbent, which would be used for capturing the other odors. So the typical solution is 2/3 Sulfazorb XL and 1/3 CPS 12 blend, which is that blend of activated carbon and permanganate media. Very, very, very powerful selection of adsorbent media, a great standard for it. 99% of the systems we send out have that combined, and the customers are very, very happy with it. So it's really great. If it turns out that you have higher levels of H2S, that proportion can be changed, or maybe you have lower levels of H2S and you need more adsorbent media for the other odors, then you could do 50-50 maybe, or something to that degree. We're recently sold a bunch of systems to a major pet food manufacturer who used only our CPS12 blend in there because they're dealing with only organic odors. They don't have any hydrogen sulfide. So they filled the entire system with our CPS12 blend media, and it works just fantastically for them. So what's the next important part about an adsorbent system? And that is monitoring the system. How do you know when the adsorbent needs to be used? So there's two ways to do that. There is a manual media indicating rod. So this rod starts off with a bright silverish color, and it will change to black as the adsorbent media has been used. And so that is what we refer to is our real-time media bed monitor. It is a manual system. It requires the operator goes out and pulls the rod out, say every month, and records how much of the rod has been consumed. We've had that in our product offering since the company was founded 18 years ago. It's a fantastic product. Customers love it, but customers really press for us to come up with something that they didn't have to go out to the unit and pull the rod. And so a few years ago, we did develop an electronic monitor, which does the same function. This product is evolving. Currently, it is a rod which does go down through the adsorbent media and has an array of sensors on it, which feed back to a PLC and basically does the same function of monitoring where the corrosion, where the reaction has occurred here, and it's actually able to feed back to the customer a date and when the adsorbent media is going to need to be changed out. And PureAir continues to evolve this product. Our next generation, I'm very excited, is about to be released, a much lower cost. It looks like we're going to be able to put this on basically every odor control system going out at very low cost. Our customers absolutely love this product because it allows them to really monitor the adsorbent system, and they know whether the system's functioning or not. So one of the things I like to say about PureAir systems is we take invisible odorous air and we purify it, and out comes invisible non-odorous air, but you can't look at it and see whether it's working or not. So it's not easy for somebody to just to understand what the exact system status of the system is without putting their nose into the outlet. And so this electronic system really is a predictive ability for the customer to not have to wait until they start smelling odor coming out of the system and then react quickly to try to change out the adsorbent media. It allows the customer to know how much of the adsorbent has been used and when it needs to be changed on a proactive basis. So, all right, so we've kind of moved and covered adsorbent systems. Of course, that's our company history is selling adsorbent systems, but we do want to address the other technologies out there as well as biological odor control. So we break this into two categories, and unfortunately, there is no standardization in the industry about the naming of these products. And so I'm going to let you know how we name these types of products. And we can argue in the industry back and forth about what they should be named. But generally, we're referring to biofilters and bioscrubbers or biotrickling filters, okay? And the general concept is that a biofilter is some type of a vessel. It could be a pre-manufactured vessel. It could be a poured concrete vessel. It could be an in-the-ground vessel or above-the-ground vessel. And inside of this vessel is some type of substrate that allows for bacteria to grow on it. So here you can see this is wood mulch. There are other products that are used for this. Some of these are coconut husks, Soil has been used to some extent. Lava rock has been used as well. So these are all very porous substrates that bacteria can grow on. And generally, you take your odorous air and you blow it into the bottom of these systems. You make sure that that air is very, very humid, because the bacteria that is going to grow on these systems to eat the odor requires a high humidity. You blow the air into the system, and as that air percolates up through these beds of mulch or whatever you're using for it, the bacteria will eat those odors. All right. This is a very proven technology. It can be a low-cost technology, but generally takes a lot of space, and the amount of time that the air has to spend inside of these systems is typically pretty high. So you're typically saying about 30 seconds of residence time for these systems. That means that the system has to be sized to allow the air 30 seconds to spend inside of here before it percolates up through the system. But in general, very effective. And there are lots of different bacteria that can grow in here depending on what odor you are working on. So typically your manufacturer of these biofilters will help you out and get the system going, but these are generally naturally occurring bacteria. And when they see the environment coming in, that bacteria will use the odorous food and they'll grow. And these systems actually won't remove any odor in the beginning, but as the bacteria grow inside of them, they'll start improving and growing and more of that bacteria, which will capture more and more of that odor. And then within typically a few weeks, these systems are removing a good portion of the odor that's coming into the system. Typically, they don't require a lot of maintenance, but eventually the bacteria that's growing on these systems, it's using the substrate here as a nutrient, and it will break it down, and eventually this mulch breaks down enough that it has to be hauled out and replaced, and then the biofilter restarted again. But very interesting technology. We have lots of customers who are using these as well. PureAir has some experience in them. They're generally not very technically, doesn't require a great deal of technical knowledge of there, and it happens to work for some customers generally with lower levels of odor to use these. Now, PureAir does work in the area referred to as bioscrubbers or bio-trickling filters. And generally, we consider these more engineered systems where you're using a very intentional vessel to hold a substrate, which is going to very intentionally grow a very specific type of bacteria in there, which is going to do a highly efficient way, have a high efficiency at removing a particular odor. So generally, most of the work that we do for bioscrubbers is removing high levels of hydrogen sulfide, and the systems that we produce are generally going to be about 99% efficient at removing high levels of hydrogen sulfide. So typically in the 100 to 300 ppm range. We can certainly work in lower range of 20. So 20 to 300 parts per million. These systems are highly efficient at removing hydrogen sulfide. Now, does that mean that they remove all of the hydrogen sulfide? Typically not all of it, because if you've got 300 parts per million and the system's 99% efficient, that means you still have 3 parts per million coming out of the system. So it removes a huge amount of the hydrogen sulfide, but there's still some left over. So we typically have paired with this an adsorber system to capture that remainder as well. The other advantage of the adsorber system after that is that, let me go back to the adsorber system after that, is that the biological system, keep in mind, is it's living organisms that are living inside of here. There can be disruptions. You've got to feed some nutrient to the biologicals to keep them growing. Temperature affects things. Water, they have to be kept up with clean water periodically and flush contaminants out. If there's ever a disruption in this system, those bacteria will be killed and the system has to be restarted. During that restart, which often can take a couple of weeks, that adsorber system nearby is able to continue to provide the odor control needed. Even at higher levels, it's able to provide backup in case the biological system has an interruption. So there's a really great technology. It can provide basically 100% odor removal with the two systems together, or the adsorber can back it up in case there's a problem with the biological system. So this is kind of a schematic showing the difference between a biofilter and a bioscrubber. The biofilter is very simple. You basically have a blower. You have some way to humidify the air. That air is then blown into the bottom of this filter media. There's lots of different filter media out there that are available. And as that air percolates up through it, the odors are captured, and any water that's collected from the bottom of the biofilter is just brought back into the humidifier typically, or sumped out and treated. The bioscrubber, again, is a more engineered system. We've got a contained vessel. We've got spray heads that are continuous in a continuous loop, spraying water and nutrient onto the packed column. The key with this technology, it's all about surface area here, and all about having a substrate which will hold up to a very, very corrosive environment. So these systems typically operate in the range of 2 to 4 pH, extremely acidic environment. The bacteria, we use a very special bacteria that's in here that we inject into the system initially that love to grow in these highly acidic environments. So this is the type of bacteria that you find naturally in geysers and hot spring pools that love these highly acidic environments. And we inject this bacteria into this environment. We also inject some acid in the beginning to make sure that this is a highly acidic environment in the beginning. This highly acidic water then circulates around the system, and the bacteria grow. Air with hydrogen sulfide enters the system. The bacteria eats the hydrogen sulfide, converts it to sulfuric acid. The sulfuric acid goes into the waste, and then we drain as the acidity gets too high, or the pH gets very low. We'll actually inject new fresh water into the system to keep that pH in a very particular range. So very, very, very interesting technology. It's a great technology for high levels of hydrogen sulfide. They have a very significant initial capital cost, but typically the operational costs are pretty minimum to them. You've got to feed it water and feed it a little bit of nutrient. And typically the operational costs are good. High efficiencies to them, but remember, you've got a very high level of gas coming in. And so even a high efficiency system is still going to have a little bit of odor coming out. So here's some comparison between biofilters and bioscrubbers. I think I've covered most of this. One of the things I didn't mention to you is the hydrogen sulfide. I mean, the residence time and for a bioscrubber, biotrickling filter is about half or even less that of a biofilter. So there's a substantial improvement in footprint there for it. But it is a more complex system. So you've got some sensors in there, you've got pumps and things. You need to be concerned about cold climates. They're typically not well suited for cold climates because you've got this liquid that's circulating that you've got to maintain at a particular temperature. The microbes like to be within a particular temperature range, and you don't need pipes freezing on you. All right, and we're going to just very, very briefly here at the end talk about chemical scrubbing. So this is an example of a chemical scrubbing. And this is basically taking a tower with a packing like our biological system and using a reactant chemical to, as the air enters into the tower, it typically enters from the bottom and it goes up and comes out the top. And there's a spray system which is reacting in here and a packing. So it allows for a chemical reaction between the gas entering the system and the neutralizing agent. So these are for odor control. Typically, it's used a caustic solution, or you might use a bleach possibly for removing these odors. Typically, they are very good for applications where you have high levels of odor and maybe high airflow, because this can be cost efficient for a high odor level and high airflow. The problem with these systems is you can see they're far more complicated. There's a lot of instrumentation, and that instrumentation is in a very harsh environment. And so trying to keep these things up and going, and any of the chemicals that are used as reactants are hazardous. Without a doubt, they're hazardous. And so your personnel are working with these hazardous chemicals, and those hazardous chemicals are typically very, very hard on all the instrumentations and the valves and the pumps and such. So I have some experience with wet scrubbers. PureAir generally does not work with wet scrubbers because we don't see ourselves as experts in that field, and because of the maintenance involved with the systems on down the road. But it can be a very good technology when chosen for the right type of application and the right organization that has the ability to maintain these properly, and to control the hazardous chemicals that are used inside of them. So they're typically focused on one gas. They typically have high concentrations of the reactive hazardous liquids. Maintenance requirements are significant, and they're typically have to be designed for your maximum gas level, typically. So you have to know what your maximum is, concentration, and design the system based on that with it. But generally, it has the lowest overall footprint per unit of airflow, and the cost for these liquid systems are typically fairly effective as well. So just taking a look at the various technologies, and I can make this presentation available to you. If you send us a quick email, we'll send you a copy of it. But taking a look at all the advantages and disadvantages, activated carbon, typically low maintenance and high efficiency. The disadvantage is the replacement can be very significant, especially in high H2S environments that you're going to be changing out very often, and you've got that degassing going on. Engineered adsorbents, typically low maintenance requirements for them. High efficiency, 99.9%, many configurations. You can also remove lots of different odors if you're layering your media, your adsorbent media. The disadvantage, you do have to replace the adsorbent periodically. We typically say every 18 to 24 months for a system, but it depends on the amount of odor coming into the system. Biofilters, the nice thing is there's no hazardous chemicals there, very low maintenance, but they do have a large footprint. Bioscrubbers, generally no hazardous chemicals. I did mention that the liquid that is being recirculated has a low pH, but in general, you're not adding anything to it, so you're not having any contact with it. It is very effective at high H2S levels. It's generally considered a green technology because we're using bacteria to remove it, to remove odor. There is some significant maintenance. You need to have some good maintenance people because there are some sensors and such and pumps on there that do wear out over time. There is some significant water consumption. So if you're in parts of the world where water is scarce, you need to consider that. And we would say generally the real world efficiency, considering maintenance practices in the industry, is typically going to be 95%. We can make them run at 99%, and we can show you how to run them at 99%. But our experience is when we go back to the customer a year or so later, they haven't kept up with the maintenance, and we're typically seeing 95%. So that's why it's important to put one of these adsorbers afterwards, an engineered adsorbent system afterwards, is to be able to capture that remaining odor that's there. And then the chemical scrubber, low footprint, lots of vendors out there for these systems, typically significant maintenance and hazardous chemicals involved. I also have a comparison, taking a look at footprint, complexity, efficiencies, capital costs, and operating costs. We'll make sure those are available to you. If you want to do a quick screen print, you've got that available to you. We're also recording this video, so I want to make sure you know that we will have it on our YouTube channel, so you can go back and look at it at any time. So generally the conclusions are total odor control is possible. And if you're doing a good job, if you're working at it, it's very possible, and you should plan for that. Selection of technology requires either knowledge of what your odor is, or you're going to have to assume, and assuming can be dangerous. We really think that the hybrid technologies are excellent technologies to consider. If you've got a high H2S application, a bioscrubber followed by engineered adsorbent systems, fantastic. Or a scavenger followed by engineered adsorbent is really fantastic as well. Maybe if you're in the 20 to 50 ppm range, a scavenger followed by engineered adsorbent is great. A bioscrubber anywhere from 20 and above, followed by engineered adsorbent is great. So just keep that in mind for some of those applications. PureAir is here to help you out with your selection, of course. So we've come to that point in time where if you've got any questions, you can raise your hand and ask. I think that we actually had some questions that came in. I've got to pull up that that screen here. Okay, so I'm gonna put those out on the screen. I don't know. Oh, I guess I can't share them as easily as I thought, but let's take a look. Ray Porter. Ray, it's good to hear from you. Ray puts out the question, odor dilutions go from very dilute to less dilute until a detection threshold is reached. This is a standard method. So yeah, thank you very much, Ray, for clarifying that. Ray's a real expert in that area of odor dilutions. And so I had indicated probably that you start off in one direction, go the other. He confirmed that we go from a very dilute to less dilute when you're looking for odor threshold, those odor units. Alex from Quebec says, can you state what a typical scavenger bed would use as the material and the contact time? Yeah, Alex, so we did show you our scavenger. There's some other products out there. I think a product that's been out there for a long time is the iron sponge. We would consider that a scavenger as well. Typical contact time depends on what efficiency you're looking at. I can tell you that in our biogas applications, we will plan for 15 seconds of contact time, but that's because they're dealing with 5,000 parts per million, and we've got to get them down to almost zero as far as that goes. And so generally, if what we typically plan for is with a scavenger bed is it's going to trim down your H2S level, and then we'd use engineered adsorbents after that in order to capture the remaining from it. So we can work with you on that time, but typically a scavenger is going to be far less efficient per unit of time than your engineered adsorbents are going to be, but they have a really nice cost to them. Let's see, an anonymous attendee has asked, can activated carbon using Chemisorption be regenerated, or does it have to be landfilled? So the Chemisorbents do have to be landfilled, because once you add the chemical onto an activated carbon, then there's going to be a chemical reaction which is going to turn your gas into a solid, and that solid really cannot be changed. The reaction cannot be reversed, and so that is in those pores permanently, and generally has to either be landfilled or incinerated. So I will mention to you that there is the option to take activated carbon, impregnated activated carbon, and it does still have some energy source to it. So it can be sent to an incinerator, so you could get some energy out of it as it's incinerated, but it is typically landfilled. Ray has had another point. If an adsorption system is used to polish a gas stream after a biological system, do you need to reheat the gas stream, lower the relative humidity? Great question, Ray. So generally, PureAir uses a line of adsorbents, which we refer to as hygrophilic. That's H-Y-G-R-O, hygrophilic. These are adsorbents that like humidity, all right? Now, they don't like water droplets, all right? But they do like humidity. And so typically, after a biological system, there will be quite a bit of water that's coming out of the system, water droplets, water mist, certainly a lot of humidity. We always do put a high efficiency mist filter after a biological system and before an adsorber system in order to keep that water from coming out. Typically, there isn't a need to heat the gas stream. There are some people out there that heat gas streams in order to dehumidify it. That's actually a false premise. You're not actually dehumidifying, you're just changing the relative humidity. So it doesn't take water out of the air, but it does increase the temperature, which can make plane activated carbon not work as well. But we do really focus on taking water droplets out, even the tiniest water droplets, to make sure that it doesn't harm the adsorbent media. Because while our adsorbent medias are hygrophilic, they like humidity, they don't like water droplets. Alex mentions that the question was later answered, but I'm glad we were able to discuss it. Lucas asks, hello, is it possible that high concentrations of H2S had restriction in bacteria activity? Well, so it's interesting, Lucas. These bacteria really like H2S, so they're at home when they're in the hydrogen sulfide. And so typically, the reason that I kind of limited 300 parts per million is kind of the top end on where a bioscrubber works. It can actually go higher than that, but the amount of sulfur which is generated at that point in time can be a little problematic. And there's a lot of special things that you have to do in order to keep that sulfur getting flushed out of the system. But in general, high H2S levels, the bacteria like the H2S. And so while you and I don't like it very much, they like it. And really the restriction is just being able to flush out all of the byproducts of the H2S capture by the bacteria. That becomes the biggest factor. Hassan has asked me to see the chat. So let me go to the chat box with that. Yeah, I see there's a number of things here. Let's see, Hassan is, do you have a log on an actual installation of a bio trickling scrubber showing H2S levels at exit in function of fluctuating load, notably peak H2S, where bacteria has not had enough time to grow to digest such levels? Such a log would be solid proof for beast design. And yeah, so I'll have to go back and take a look at that. I don't think that we have logged the H2S as we have brought a system up, but we have one that's being activated shortly, one in Illinois. So I think we could work on capturing that data. That's a great point. I appreciate it. Samir mentions we would like to get an introduction regarding the ecology units for kitchen applications. So Samir, we'll be happy to work with you on that. We could probably do a whole separate webinar on that. Yusuf will be able to help you out with that without a doubt. So thank you very much for your on that. I'll copy your information and send it to Yusuf there. Wei in China mentions biofilter removes odor by bacteria. Does the bacteria generate its odor? Really good question, Wei. Yes, it can. So bacteria, that's another great reason for having an adsorber system after a biological system, is because the bacteria itself can create kind of a musty smell. And the bacteria doesn't remove all of the odors. It removes a lot of the odors, but not all of it. And so having that adsorber system to capture even the odor that's created by the bacteria is very important. So Wei, thank you very much. That was a very, very good question. I should have mentioned that in my presentation. Dave asks, Kevin, well, he just says, I have another meeting. Thank you for the presentation. So Dave, looks like Dave's off again. And Alex has a thank you for us. Let's see, back in the questions. Let's see, Lucas, Hassan, last question. It looks like John Venegas says, do you see a move towards IIoT or IoT type instrumentation becoming more prevalent in systems today? are more measurement points being incorporated into the spec for smart type systems, monitoring for alarms and system set point annunciation. Absolutely, John. I appreciate you mentioned that. Yes, you know, IoT, the Internet of Things, everybody needs to get ready for it because there is a lot of data that's out there and floating around, and our electronic bed monitor is one of those such devices. It does have a wireless capability to it, so it is able to talk to things around it. And I do see there's a big trend. Everybody wants everything to be automated. I have to mention to you that the odor control industry in general is far behind a lot of the rest of the industry in the wastewater environment, and has far less reporting of the performance of the system. So we're very excited about how the electronic bed monitor from PureAir plugs in IoT capability into this environment. So John, yeah, I do appreciate it, and I agree that that's going to be a big thing in the future, being able to get everybody plugged in. All right, well, thank you very much, everybody. It looks like we're at the end of the questions. You certainly know how to get a hold of us. You can reach us at info@pureairfiltration.com. Please let us know how we can help you. It was my pleasure today to present this to you. It's and we're here to help you however you need, whether it's our products or whether you just have other questions about it in the industry. We'd be more than happy to answer your questions. So feel free to reach out. Everybody have a great remainder of your day, or if you woke up in the middle of the night to watch this, thank you very much. Head back to sleep. Take care now.